So what we're going to look at next in regards to exponential functions has to do with a special type of exponential function, and that's what's known as the natural base. So the natural base, sometimes it's called the natural exponential function, and it's y equals e to the x power. And this e here, the base of e, is what's known as Euler's number. And Euler's number, similar to pi, is an irrational number, 2.71828, etc., etc., etc. And the natural base is especially important in a lot of different things that you'll do next year in calculus, but what we're going to focus on for right now is some different things with computing interest, specifically computing what's called compound interest. So this is what the graph of the natural base looks like. So just keep in mind that this function here, this is really like saying 2.71 dot 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 to the x power. That's what that value of e looks like. So it's very similar to some of the other exponential functions, particularly 2 to the x power that we looked at from the previous lesson. So as far as just some different things with your calculator goes, we're going to take this y equals the natural base to the x power, and we're going to substitute these values in for x and see what we get here. So similar to what we did with some of the previous exponential functions, we'll sort of take these to sort of 3 places here. So if I come out of this, pick up my calculator. So first, if I got x is -2, so one of the things to notice about your calculator here is if you look in blue above this ln button, and this ln button stands for the natural log, which we'll get into looking at in a couple of days, but in blue above it you have e to the x here. So if I do the natural base, e to the x power, and I put in a -2 for x, this is going to come out to be roughly 0.135, we'll call this. Okay, so that's for part A. For part B, if I put a -1 in for x, so I'm going to do the same thing here. I'm going to get second natural log, so I get the natural base to the -1 power. And when I do that, I get 0.36, we'll call this 0.368. 0.368. So that's for part B. For part C, if I put a 0.25 in for x, so if I take the natural base to the 0.25 power, that's going to get me, if we're going to go to 3 digits here, that's going to get me 1.28 for part C. And then for part D, if I put a -0.3 in for x, so if I do the natural base to the -0.3 power, I'm going to get here 0.741, we'll call this 0.741. So that's for part D. So as I kind of move forward here with some different things involving the graph of the natural base, so notice here I have for part A 2 times the natural base to the 0.24x power. So if I put this in my calculator just to get some values from the table here, so you notice I got for y1, let me sort of turn this one off for now, and if I graph this just to get an overall view of what that graph looks like, and if I go to my table just so I can get some points here, notice I only really have one point that I have the exact value here for 0, 2. So I'm going to sort of pick a couple points where I'm going to have to do some estimating here. So I'm going to use this point here, -1, +1.5. I'll use 0, 2. And then we'll maybe use this point here, 1 and 2.5. So if I come back to here, I'm just going to make a little XY table off to the side here from some of those points that we got from the calculator. So if I take this here, I'm going to use -1. That came out to be approximately -1.5. And I had 0, 2. And then I also had 1, and that came out to be approximately 2.5. So if I get those points on the graph, I got -1, -1.5 might be right about here. I got 0, 2, which is going to be here. And then I have 1, +2.5. That's going to be here. I think this was supposed to be +1.5, this value here. So that's going to, let me take this, erase that point there, and move that up to +1.5. So that's going to be right about here. So now all I want to do is I just want to run my curve through those 3 points, and kind of already knowing what the shape of this is, I get a pretty good idea what that curve's supposed to look like. So that's what the graph, or the sketch of the graph for part A. So now if I go to part B and I do the same kind of thing here, let me go back to y equals, and I'm going to turn this graph off. And I'm going to turn this second part on here. So just real quick, here's what the graph of it looks like. So notice it's coming from left to right. It's decreasing as I read it. And if I go to my table just to get a couple points here, so I'm going to use here, let's see here, I'm going to use maybe this point here, -2, +1.5. I got 0 and 0.5, I can use that one there, and then maybe I'll use this one here, 1 and 0.27, we'll call it maybe a quarter, something like that. So if I just draw a table here for those values, so I got x and I got my y here. So I'll put in -2, -1.5. My point in there. I got 0 and 1/2. And then I also have 1 and 0.27. So if I go to get those points on the graph, I got -2, negative. Where's that positive again? Let me double check that. Keep this up here. So that's +1.5, yeah. So let me fix that again. Right, this should be +1.5. So when I put that point on the graph, -2, +1.5 is going to be right about there. I got 0 and 1/2, that's going to be right about here. And then I have 1 and 0.27, that's going to be right about here, real close to the axis there. So once again, I got 3 points. I kind of know what the shape of this is going to be already, so I just want to try to draw my curve to go through those points there, just like that. So that's sort of a sketch of what part B is going to look like. So in terms of some things that we use the natural base for, we use the natural base particularly when we're talking about computing what's called compound interest. So in terms of how you compute the value of the interest when you're talking about an interest rate with a principal and a time. So if we're talking about having your interest compounded so many times in a year, this is the formula that you would use for that. A stands for, in this case, the balance in your account, and that's where this is here. P is the principal, that's how much money you have in the bank. R is your interest rate. Just remember, always convert your interest rate to a decimal when we're talking about formulas here. N is how often your interest is compounded per year. So for instance, if your interest is compounded monthly, then your value of N would be 12, because if it was compounded monthly, then your interest would get compounded 12 times in a year. And then T is the time, the amount of time that your money is in the bank. So that's if your interest is compounded so many times per year. If your interest is compounded continuously, and by continuously we basically mean if your interest is compounded if your interest is computed every second, then this is the formula that you would use for that. So we have balance equals, and that's A for what the balance is, principal times the natural base to the R times T power. So the next example kind of focuses on some of the different things here as far as how interest is compounded. So if I compound my interest quarterly, so if you notice here, the question says a total of $12,000 is invested at an interest rate of 9%, and what's the balance after 5 years? So A, B, and C sort of give you some different options as far as how often your interest is compounded. So if for part A, if your interest is compounded quarterly, that means your interest is compounded 4 times a year. So in this case, your value of N would equal 4. So the formula, I have A equals P times 1 plus R over N to the N times T power. So if I just substitute my values in here, I got a value of P of 12,000, and this would be 1 plus, the interest rate is 9%, so that'll be 0.09, divided by 4, that's how often your interest is compounded, that's n, and then to the n times t power would be 4 times 5 years. So if I take that, and I'm going to use my calculator to sort of do the computations here, and I'll show you how to do this in a real quick and easy way. So if I exit out of here, and if I come into this, let me go to my calculation screen here. So now I have 12,000 times 1 plus, I'm going to get my little fraction key up here. So this will be 0.09 divided by 4. Let me delete that real quick because I want to get over to here. And I'm going to take this to the 4 times 5 power. And when I do that, that makes my balance $18,726.11. So that's what your value would be after 5 years at 9% interest if your interest was compounded 4 times a year, if it was compounded quarterly. Now for part B, the question says the same sort of thing, except what if your interest was compounded on a monthly basis instead of a quarterly basis? So monthly basis would be n equals 12. So when I go to do my formula here, I got A equals 12,000 times 1 plus 0.09 divided by 12 now, since I'm going to do it 12 times a year, and this would be to the 12 times 5 power. So when I do that in my calculator, so once again I'm going to sort of exit out of here, and when I do this I'm going to just do my second enter here just to get the previous formula up, and then all I want to do here is just take my 4s and I want to change them to 12s. So let me start with the fraction here. So I'm going to put a 12 in there, I'm going to take this 4, I'm going to put a 12 in there, times 5 at the end. And when I do that, I get a value of $18,788.17. So one thing to notice about this is that I still had the same amount of money, I still had the same interest rate, and I still had the same amount of time that the money was in the bank. But because my interest was computed more often, it was done monthly instead of quarterly, the amount in the amount of the balance does increase. It increases by about $62. So just from having your interest compounded more often, it has your balance being something a little bit more. And then if I go to part C here, if my interest is compounded continuously, meaning if my interest was compounded every second, I'm going to use the formula for compound interest this time, and that's PA equals P to the natural base to the RT power. So when I substitute those values in, this is going to be 12,000 times the natural base to the 0.09 times 5 power. So if I put that in my calculator, I come back to this here, so I have 12,000 natural base to the 0.09 power times 5, which is the time. So notice I get a value here of $18,819, and this would be 75 cents. That 6 is going to round this 4 up. So if you notice the trend here that sort of happens, and that is the more often you have your interest computed, the more often it's compounded, the more money you ultimately get. So this was quarterly, this was monthly, and this was by the second. So the more often your interest is compounded, the more often your interest is computed, the higher the balance is going to be because of that. So That's one of the more practical uses that we're going to take a look at in regards to some different things involving the natural base.